Next is an important topic uh, which we come across quite often. That is deriving system equations for systems where we have derivative causality in our bond graph models. Now, I discussed with you that derivative causality, it indicates that the model is either incomplete or it is wrong. Okay, but sometimes uh, we uh, approximate things. Uh, we understand that we are not going to add the additional dynamics that is needed to rectify the causality. Let us see how the system equations would behave, would look like. So let us see how we derive system equations in the presence of derivative causality. So we have taken this very system which we had taken as an example for modeling derivative causality. So we have this spur-gear system. You are already familiar with it. When you causalate in this manner, this I element goes in integral causality and this I element goes in derivative causality. So if you do the causal strokes for this bond graph, this is the pattern of causality that you obtain. How do you derive equations for this system? It's the same algorithm that we follow. Please note the steps. So we start with the first, what do the sources give to the system? What does this give to this? It gives effort 5. So, effort 5 is the same as this torque 1. Okay. Next is flow 1. What this I element is giving to this system, it is flow 1. And this flow 1 is P1 upon J1 in terms of its parameters and states, it is P1 upon J1. Then what does, then we have effort 2 dot. What does this I element give to this system? So you can see it gives effort 2 dot. But this is not a state which is contributed by this I element, and it will become clear to you why it is the case. Okay. So while I have put this P1 in rectangular box, I've not done that for P2 because it's not contributing a state. It is dependent on something else. Let us have a look at it. Proceeding further, we have uh, yeah, so we proceed to the next step, that is what does the system, what does the system give to the elements? So in that case, let us start with this. What is the system giving to this I element? So it's a derivative causality element, but still we ask a question, what does the system give to this I element? And you can see that it is giving flow 2. Flow 2 is the same as flow 7. Okay. So flow 2 is the same as flow 7, and flow 7, in fact, flow 2 can be written as P2 by J2. P2 by J2, that is in terms of its own state and parameter. And this flow 2 is actually flow 7 because it's coming from this one junction. So flow 2 is the same as flow 7, and it can be written as mu times flow 6. Mu is minus n1 by n2 into flow 6. Flow 6 is the same as flow 1, which is P1 upon J1. Okay, so you know this entirely. So flow 2 is the same as flow 7. Flow 7 is minus n1 by n2 times flow 6, and flow 6 is the same as flow 1. So this is completely known. So when you make this substitution here, you get flow 2 is equal to P2 by J2, which is in terms of its own state and parameter. And that is equal to minus N1 by N2 times P1 by J1. So if you look at this equation, it's an algebraic equation. It's not a differential equation. It's a simple algebraic equation. But what it is telling you is that P2 is related to P1. So P2, the variable P2 can be written in terms of the variable P1. Okay. So one can substitute P2 in terms of P1 uh, in this case. Now let us proceed to the second step. So the question is, what does the system give to this I element? It gives effort 1. Effort 1 is a rate of change of momentum associated with this I element. So it is P1 dot, and P1 dot can be written as E5 minus E6. So E5 minus E6 is P1 dot. Then what is E6? E6 is actually this effort, and we know from the transformer relation that this effort is mu times this effort. This flow is mu times this flow. This effort is mu times this effort. So it becomes effort 6 is equal to minus N1 by N2, which is this mu, into effort 7. Effort 7 is here. So effort 6 is equal to mu times effort 7. And effort 7 is the same as this effort. It's coming from here, effort 2. And effort 2 has been worked out earlier as P2 dot. So we can write P1 dot as tau 1, that is effort 5. It's effort 5 minus effort 6. So effort 5 is tau 1 minus effort 6. Effort 6, we have already seen it's minus N1 by N2 into effort 5. So, uh, effort 6 can be written as minus N1 by N2 times P2 dot. So if you now write, P2 dot in terms of P1 using this expression, if you make use of this expression which you have already derived and replace P2 dot with it, if you differentiate this, you see J2, J1, N1, N2, they're constants. So you have P2 dot related to P1 dot. So instead of P2 dot, you can write it as minus N1 by N2, the whole square, into J2 by J1 into P1 dot. Now you can see that left hand side also has P1 dot, right hand side also has P1 dot. So you can take this derivative term to the left hand side and write it as 1 plus this term into P1 dot is equal to tau 1. Now you can write this left hand side as a total derivative also. If you write it as a total derivative, okay, you can see that this part in this bracket is constant, and this is rate of change of the angular momentum. So here you have J. So this is angular rate of change of angular momentum of 1. So here you will have J1 into omega 1. But there is this additional term which is coming in, and that additional term is because of the derivative causality. Okay, it is because the momentum of one, you see this momentum of this gear has got dependent on this momentum of this pinion. So it's an algebraic relation which is, so one can be written in terms of the other. So this angular momentum can be written in terms of angular momentum of this gear. And so we can write this part here, and this part which is shown in the brackets, it's a constant. and it happens to be the equivalent inertia, because this inertia, when it is multiplied with angular velocity 1, that is the angular velocity on the pinion side, uh, it gives you the same effect as if these two are coupled using this spur-gearing, and uh, the rate of change of this combined inertia multiplied by angular velocity 1 is caused by the torque that is acting on this link. Okay, so the effect of this derivative causality was that its inertia got dependent on this inertia. So its state, it could not contribute directly. It had to surrender its state, and that state got clubbed up with this because you are interested in the angular velocity on the pinion side. So you can write this expression in this form. Now it's also possible for us to do the so I hope this step is clear to you. So this part actually, you can see here, you have the equivalent inertia, which is moving with angular velocity omega 1. So this together is going to provide you the equivalent angular momentum, the rate at which this combination is moving, a rate of change of this as if it is moving with angular velocity omega 1. And that is caused by the torque tau 1 that is provided on the input side. So here, in this case, the inertia of the gear is referred to the pinion side. Okay. This is a simplified bond graph. If you eliminate the derivative causality, you can take away the I element from here and shift it here. But when you shift it here, its effect is that it results in the addition of this term over here. So this is a simplified bond graph model after elimination of the derivative causality. So you remove this I element and you transferred its effect over here. So this is what we have taken from here. This is the equivalent inertia, as if it is moving with angular velocity omega 1. Okay. So you have the torque 1 acting on this. If you were to consider a load torque, that could be applied over here as well. So right now in our system, this is what we have done. This is how we have eliminated the derivative causality by shifting, by referring this inertia towards the other side, towards the side which is moving with angular velocity omega. Now let us consider the other possibility of causality. If this I element is integrally causaled, not this I element. This I element goes in derivative causality. This goes in integral causality. If this is the case, this is the second case. Okay. So in this case, the causal pattern for the transformer would appear like this. Okay. And this I element here will go in derivative causality. So the state cannot be contributed by this I element. So we have placed this one in a rectangular box because this is the only state that can be contributed by this I element. So the procedure for the derivation of system equations remains the same. But when you do this substitution, here you will find that the rate of change of this angular momentum. Okay. This, what does this system give to this? It gives rate of change, it gives effort. Effort 2 is rate of change of this angular momentum. And this is equal to effort 7. This is the same as effort 7, which is equal to minus N2 by N1 times effort 6. And effort 6, you can see here, is actually effort 5 minus effort 1. So effort 6 is effort 5 minus effort 1. And effort 1 we already know as P1 dot, which is the derivative of this of the electrical I'm sorry, of the angular momentum of the pinion side. So we have this relationship. We can substitute it here. So P2 dot is equal to effort 7, and that can be written as minus N2 by N1 into tau 1 minus P1 dot. Okay, from this equations. And P2 dot, you can now write, if you do this substitution, okay, what does this system give to this I element? You will get it as minus N2 by N1 times this expression. Here you have on the left hand side P2 dot, and also on the right hand side you have P2 dot. So you can take P2 dot towards the left hand side, and when you do that, you will be able to obtain the uh, equation of the same system, but in terms of the angular momentum, equivalent angular momentum, assuming that it is on, assuming that that angular momentum is related to omega 2. Okay, so here you have another equivalent inertia, um, which comes here, and this equivalent inertia multiplied by omega 2 becomes equal to this tau, this mu into 1 upon mu into tau 1 plus tau L. Okay, so this is the equivalent inertia when the I element with derivative causality is referred to the side with angular velocity omega 2. So this is the second possibility. Okay, here also now we have removed the derivative causal I element and transferred its effect on this side. Okay, its inertia has come here. But when you did that, you had to add this term, which is minus N2 by N1 square into J1. Okay, was reciprocal of this square of that and multiplied by J1, which was the angular velocity, which was um, the moment of inertia associated with the pinion. So you can see that the effect of the moment of inertia of the pinion gets transferred on this side using this leverage. So it is N2 by N1. You can see that it is more. It is N2 by N1 is greater than 1 in this case, and you're dealing also with the square of it, and that is added to that is multiplied with J1. So J1, that is the moment of inertia of this pinion element, that gets scaled up while it is referred on this side. Okay,